Take a look at the center of the periodic table. This dense block of elements is known as the transition metals. Typically, this is where chemistry gets loud. These elements are highly reactive. They form brilliantly colored compounds, and their oxidation states undergo wild fluctuations, bouncing anywhere from a +1 to a +7 charge. But sitting right at the edge of this chaotic neighborhood is group 12, zinc, cadmium, mercury, and copernicium. They physically belong to this block, but they follow almost none of its rules. Their chemistry is so restricted and their reactions so rigidly controlled that many chemists argue they shouldn't even be classified as true transition metals. Yet, despite that quiet chemical profile on paper, their real-world interactions are intensely complicated. We rely on them to keep our human cells alive and functioning, but we also treat them as severe and dangerous biological hazards. To understand how these 4 elements can be so stubborn in the lab, but so impactful outside of it, we have to look at the strict atomic structure they share, and then trace what happens as we travel straight down their column. This atomic model shows the defining architectural feature of every group 12 element. They all possess a completely full inner d orbital, packed tight with electrons, and exactly 2 loose electrons sitting in their outermost s orbital. That packed inner shell is incredibly stable. It prevents the elements from readily sharing those inner electrons, which immediately dials down their overall reactivity compared to their neighboring transition metals. When they do react, they almost exclusively shed those 2 outer electrons. The inner d orbital stays locked away. Because of this, group 12 elements rarely fluctuate. They settle firmly into a predictable +2 oxidation state. That rigid +2 baseline is the chemical anchor for the entire group. No matter how heavy the atoms get as we move down the column, that underlying rule stays exactly the same. We begin our physical descent at the top of the column with the lightest element in the group, zinc. Because zinc so stubbornly holds to that stable +2 charge without misfiring into other reactive states, it rarely causes unpredictable chemical cascades. Evolution took advantage of that reliability. Biological systems adopted zinc as a crucial tool, making it absolutely essential for cellular division. But watch what happens as we step exactly 1 space down the table. This chart tracks the jump to cadmium. Notice the immediate, sharp upward trend in both atomic mass and physical density. Cadmium retains that same predictable +2 chemistry, making it highly prized for manufacturing batteries and pigments. However, that increased mass and a slight shift in how it binds to proteins introduces a severe complication. It is highly toxic and requires strict industrial regulation. A single step down the group takes us from an element necessary for life to one that can destroy it, all while operating on the exact same underlying orbital mechanics. Continuing down the column, the physical trends hit an extreme. As we land on Mercury, the atomic density is incredibly high, yet the metallic bonds holding the atoms together become surprisingly weak. Look at how this melting point metric plummets. The result is a bizarre physical reality. Mercury is the only pure metal that exists as a liquid at standard room temperature. Its ability to flow, evaporate, and easily absorb into living tissues makes that toxicity far harder to control, leading to decades of public health controversies and severe environmental damage. Finally, we reach the absolute bottom of the column, copernicium. This is a synthetic, heavily engineered element created entirely inside particle accelerators. It is highly radioactive and decays in fractions of a second. It exists as the volatile frontier of group 12, marking the absolute physical limit of what we can actually observe in this family of elements. Pulling back from these individual stops, a clear system emerges across the entire group. The descent from zinc down to copernicum demonstrates that the periodic table is a predicted spatial map. Where an element sits geographically dictates exactly how it will behave. Because they all share a completely packed d orbital, their reactivity is capped, ensuring they always stand apart from the chaotic transition metals next door. But as atomic mass builds and metallic bonds fray toward the bottom of the column, the way these elements physicalize in the real world changes dramatically. It is a perfect display of chemical cause and effect. The exact same electron arrangement provides the architecture to sustain human life. the stability to power heavy industry, and the structure of a deadly liquid poison, determined entirely by its coordinates on the map.